So sort of time. All right. So can they hear me? Can people hear me? Assuming people can hear me. We have a full house again today. It's cool. Start my video.
They're responding that they can hear you.
Okay.
Because I went to my desk and there's someone here and I'm too.
Oh, there's my.
Thank you. I should have done it the opposite.
There's somebody at the door.
Brittany's getting them.
Brittany. All right. All right, let's get to work. We have 97 slides to get through today. We had 97 last Tuesday, so about the same number of slides to get through. Some familiar faces. Some people I didn't see last week. Everybody doing well?
The training blew up last week. Other than that, we're doing good.
Who blew up?
The transmission.
It blew up last week?
Yeah, so I didn't make it. Thank you for having it online because I.
Oh, your tranny blew up. Oh my gosh. Yeah, that's not cool. Trannies aren't cheap.
Now I have this.
What happened since we talked last?
We had a break.
We had a break. Hopefully everybody got caught up in their studies. If you didn't, don't worry about it. You know, just stay. Don't give up.
Can you share the other screen?
Share what other screen? There's two screens to share. Let me share that one. We're shared now? All right, so since last week, what happened? I was in Toronto, not during the thing that happened yesterday, which is kind of scary. I was there on Thursday, Friday last week. Same time they had game, 4 or whatever, for the Toronto Bruins. Oh my gosh, anybody ever been to Toronto? 2.6 million people live in that town. That's a huge place. And I think it'd be a really great place to visit. But if you got like business to do there, you got like places to be. Oh, it took me an hour to get like 6 blocks out of town, to just get out of town to get to my, then I had another like 10 miles to get to my hotel. But anyway, that was that. Yesterday I gave a couple hour lecture to Minnesota State Mankato. Any Mavericks in the house? Gave a lecture to the students there about information security, and I almost feel like I'm begging. You know, I tell people, please get into this field, right? I mean, we need more people. And what happens is, you know, the ones of us who are in this field, I think we're working so freaking hard that, you know, some of us are burning out, you know, so we really want more security people. And just encourage them. It doesn't matter if you're technical or not technical. I think it's easier to learn security if you come from a technical background. But even if a non-technical background, there's lots of stuff for us to do without being, you know, technical. So that's about it. And then, you know, today we got the presentation. We'll get through this today. This one chapter, this one domain is a, you know, if you haven't started reading this, it's a big one, right? There's a lot of stuff for us to cover. So today we kind of left off, I think, with like security models. We went through that really quick. I didn't spend a lot of time digging deep into those, but those are all things that you'll have to memorize. Certainly Bella Padula and BIBA and the big ones. You'll need to know Red Book, Orange Book, you know, that kind of stuff. Certification, accreditation, you'll have to know that stuff. So has anybody are we making copies of these slides available?
Yes.
Everybody, and so you've been getting the slides? Okay. Hopefully, you know, some people, if you take the slides and maybe put them into like use them as like flashcards or something, or put them into flashcards, whatever it takes, because so much of this class is just memorization. You just have to memorize, you know, and fight through it. Today we'll get through some system architecture stuff, pretty high level things, and then we'll get into encryption, which is my favorite. We're going to get through the history of encryption, and then we're going to stop. And then, you know, on Thursday, we'll pick it up from there and finish off encryption, and then we'll get into physical security. Physical security is super easy to relate to because you can see it and touch it. It's really kind of a pain in the butt to assess physical security because you have to take into so many factors that most people don't think about, like crime rate of the area, right? You expect Here we're in Minnetonka, pretty low crime rate area, so you don't see bars in the windows, you don't see guard dogs, you don't see a gate, you don't see all those things. Whereas if we were in South Minneapolis, right, some parts of South Minneapolis or East St. Louis, or, you'd expect a lot different physical configuration. But anyway, we'll get through all that stuff. This is where we're at. So far we've gotten through chapters 1, 2, and 3. Now, if you haven't noticed, the chapters are a little bit off from the domains. Right? So chapter 1, there is no domain associated with chapter 1. Chapter 2 of the book is domain 1, you know what I mean? And so you're kind of a little bit, you can get funky. We've gotten through chapters 1, 2, and 3, and we've started into chapter 4, which would mean we've gotten domain 1 done, domain 2 done, and part of domain 3. And that's kind of where we're left off so far. How many of you are reading? You had a Thursday off, and, I guess the weather was nice this weekend, so at least here. So it was like, man, I don't know if I'm going to read nothing this weekend. But if you did, that's good. A lot of reading. Any questions so far? Anything you guys have read? Anything I can address directly with anything that wasn't clear so far? Okay. Again, this is where we're at. These are the domains that we've covered so far. We'll start off again with a quiz, kind of just to ease us into, what we're going to be talking about today. These are all quiz. I'm not creative enough, or I don't have enough time to create these custom, kind of quiz questions. So if you look at the end of each chapter, these are the same questions that come out of there. I'm just not going through all of them. So what type of memory is used often for CPU registers? Do you remember the CPU registers? There's level 1 and level 2 cache on a CPU. This is actually memory that resides on the CPU. Dynamic RAM, firmware, ROM, we can eliminate, and this is going to be pretty common in your test. You can eliminate firmware. That's not actually a type of memory. ROM is read-only memory. We'd find that on a BIOS. We wouldn't find that on the CPU or the register, so you can eliminate that one pretty quick. So then it's memorization time. Is it DRAM or is it SRAM? DRAM? It's actually SRAM. See, you just have to memorize it.
You meant to say it's letters.
Because one of them. Yep. Because one of them is capacitors and the other one's flip-flops, right? And so you have to memorize that too, and we're going to get to that in a second. So ISO 17799, which used to be BS 7799, it became BS 7799, and then it became ISO 17799. Became what standard? 27002, that's correct. Yep. 27000 isn't actually a standard, it's that series of standards. 27001 is the actual ISMS standard. If you were going to go for certification, that would be the standard you'd use. ISO 27002 is the management techniques. That's the actual standard. So which of the following describes the duty of a data owner? Data owners don't actually do anything per se. So patching systems, they don't do patching systems. That's a custodian. Which one did you say? D. A little bit of, okay. So here, reporting suspicious activity, that'd be a user, right? So if you think of those three roles, data owner, data custodian, and user, reporting suspicious activity is typically a user function that we train them on how to report, suspicious activity. So A and B you can cross off right away. You could make a case for C and D for the owner, right? Because an owner, in some cases, I want to make sure that my files are backed up, right? This is critical information, so I would ensure that. So I think C and D are both correct. The corrector answer, and you'll see this on the test too, is which one is the most correct. It would be D, right? When it comes to information security. But you could certainly make a case for C. Which control framework has 34 processes across 4 domains? COSO, COBIT, ITIL, or Octave? COBIT. Yeah, and that's just a memorization thing. Which managerial role is? Last time we did like a poll or something like that, and I had to wait for Brad because he was slow. But now we're not doing it. I just went through it fast. It's cool. I like it better this way. Just me. Which managerial role is responsible for the actual computers that house data, including the security of hardware and software configurations? Custodian owner, data owner, mission owner, or system owner? D? Yep. You get the reason why that is? right? Again, we talked before in the last class about system owners, business owners, application owners, data owners. There's different types of owners. At the end of the day, the way to determine an owner from a custodian who's ultimately responsible for the thing. If the thing fails, if the thing works, if somebody compromises the thing, who's that person who relies on that thing to get the job done, right? And that would be an owner responsibility. The custodian is just a keeper, according to what the owner, requires. All right, so what type of relatively expensive and fast memory uses small latches called flip-flops to store data? Again, you can cross off EEPROM and SSD. Those are types of data, but they don't use flip-flops. It's either DRAM or SRAM. So again, we have to remember which one? DRAM. Ooh, I heard somebody else say SRAM. All the SRAMs get on that side of the table, all the DRAMs on that side, and we're going to fight.
Story. Between that one and the DRAM, which one has the capacitor, but sandals and flip-flops both start with an S. There was SRAM and flip-flops, like sandals and
yeah, all right, that's a good way to remember it.
Yep.
The other one's by default. There's also another clue here too, because in the previous question, you'll see this on the test, you'll remember something that you had earlier and be able to play it here. Because we talked in question 1, I think, was CPU registers, right? And we know that if it's on, the closer it gets to the CPU, the more expensive that memory is. And here we have expensive. The last answer was SRAM. That would make this one also SRAM. But I think that's a great memorization tool. Sandals, SRAM, right? So flip-flops is SRAM.
Well, I'll remember that now.
Yeah, right? Encourage you guys too to share if you have these memorization techniques. Share them. I only shared like the BIBA one because I'm not good at memorizing stuff. So BIBA is integrity. Bellapagel then would be confidentiality. What type of memory stores bits in small capacitors? See, I go the long way too about memorizing things. Like we talk about the OSI model. Like they have all those. What do they call those when they acronyms or whatever? No. Mnemonics. Yeah, see, I never memorized it. I remember always memorized the actual words: application, presentation, session, transport, data, and physical. Did I get them all? Yeah. Right. So the other one was flip-flops. This one would be the DRAM, right? This is the capacitors.
And this one is D-cell batteries drains, so do capacitors.
See, you're going to do great on this. Seriously, I mean, memorization. Memorization is a big thing. So that's our quiz. That gets us a little bit kind of back into the flow a little bit. And so, okay, so say that again so I can say it for the people online. You think of capacitors, batteries, D-cell, DRAM, right? That's kind of the thought process. And then the other one was flip-flops, sandals, SRAM. Okay, yep. All right, so session 4, here we are. This is where we left off. We left off at this page, 116, if you're in the book and you want to get there. These are the things that we've covered so far. So we did cover security models. Now, when you look at all the concepts that are the things to master in this book, on that first page of this of this entire chapter, this is only half of it, right? There's a whole other half, which we're going to get to still in this class, because we'll start talking about encryption, which is the beginning of that second half of all this stuff we have to memorize here. But we'll talk about secure design concepts, secure hardware architecture. We don't have to get deep. We'll go over the stuff that we have to memorize and have ready for the test. Most security people, who are CISSPs aren't electrical engineers. We're not deconstructing computer systems and building computer systems. There are some of us that do that. I'm not one. Secure operating system and software architecture, virtualization, distributed computing, cloud is a big thing, obviously, today. System vulnerabilities, threats, and countermeasures. That stuff is sort of fun. I can maybe, if something comes to mind while I'm going through that, of an incident that I worked on recently, I'll bring that up, or one that I know of. Otherwise, it'll be somewhat dry, maybe. All right, so layering. How many network people in the room? See, I'm a network guy. I grew up a network guy, so I know the OSI model, really well. I know, where certain components play. I know where drivers are. I know all that stuff. This is the same kind of concept, but taking it to, systems, right? So you talk about layering. Layering, really, we would use layering to try to simplify things that happen at different parts of an operating system or different parts of a network. And we would obscure, we would encapsulate things that happen at one layer from the things that happen at another layer, right? And it makes it really easy if I'm like an application developer, I can just write towards the next layer down. I don't have to write drivers and everything else into my application. The same concept applies here. The 4 generic soft security architecture layers: hardware, kernel, operating system, and application. So we'll need to know what things happen at each one of these layers, just high level stuff. The biggest one is the kernel. The kernel contains the reference monitor. The kernel enforces the security policy for the system. The kernel is kind of the king in the architecture for everything else. The operating system runs in the kernel. Different operating systems would have different kernels. There's 2 different types of kernels. We'll talk about that. And then applications right on top of the operating system. But if the kernel is the core of the operating system, if the reference monitor isn't well built, if it's not secure, everything else is insecure. And if the core of something is insecure, everything else is insecure. Like NP4, that kernel was inherently insecure. And they kept patching and service pack and patching and service pack. We're never going to make that secure. And every new operating system comes with a new kernel and one that's, inherently more secure. But the kernel really is the biggest, most important part of the architecture. So abstraction and complexity, this is what I was talking about. So something that happens at one layer should be obscured from the things that happen at another layer. There are interfaces between layers. Sometimes we call them calls or system calls. Sometimes when 2 applications are communicating with each other, there's an application programming interface. That would be the interface, whatever. The same concept works. And one of the things to remember in information security just in general is complexity is the enemy of security, right? Always. It's easier to secure a 1-step or 2-step process than it is to secure a 23-step process. If you take a 23-step process and break it down into a bunch of little 1 or 2-step processes, that's also easier to secure because I only have to focus on each one of those processes and then their interaction together. So if you just remember complexity is the enemy of information security, that's the truth. This is just, and it's the same thing that comes from the book. It's about, when a user double clicks the MP3 file, the user doesn't know all of the things that happen for that audio to play. The user doesn't know when the drivers are loaded or how the drivers are loaded or how the codecs are, inserted. None of that stuff. They just see the double click and the audio works, right? But there's a lot of things that happen in between that, and that's all that layering that happens. Yeah.
Can you go back and define more clearly what a kernel is different from an operating system?
Well, you shuck the corn. Those things that come off, those are kernels. And you can eat them before they get hard. What was the question again?
What is a kernel? I hear the term, and how can we conceptualize it?
So the kernel's job is it separates the operating system from the hardware. It loads drivers. The kernel's one of the first things, if not the first thing, that's loaded from the boot sector of a hard drive. So when your computer boots up, the BIOS goes through the self-check, and then it looks for the boot sector, and then the boot sector is a pointer to the kernel. The kernel then loads the rest of the operating system. That's what the kernel essentially does. So abstraction, you understand abstraction? What happens at one layer is abstracted, obscured from what happens at another layer. So then we have this concept of the ring model. This is a theoretical concept. There are no specific rings, built into an architecture, but it's. No putting a ring on it. Now I gotta, and for that I have to have a drink of my energy drink. All right. So CPU, hardware, layering. These are the layers of the CPU. So the kernel runs at ring 0. The operating system components outside of ring 0. In practice, there are really only 2 rings that are used: ring 0 and ring 3. Ring 0 would be kernel mode, what we would call a kernel mode. That's where the operating system runs. That's the lowest level, that's the most sensitive level of the architecture, and the other would be user mode, right? And user mode is typically ring 3. So in practice, really there's only 2 rings that are typically used, ring 0 and ring 3. Other things that might run in ring 0 might be antivirus, might be some endpoint protection products, might be some application whitelisting things. They would run kind of alongside or with the operating system and the kernel running at ring 0. But if there's a vulnerability in something that runs at ring 0, then you could potentially bypass the kernel, right? There's a channel there. But anyway, in the traditional 4-ring architecture, ring 0 would be the kernel, ring 1 would be operating system components outside of ring 0. I can't think of anything off the top of my head that would run in ring 1. Even a hypervisor, when we talk about virtualization, a hypervisor typically runs at ring -1, which means it runs lower and the operating system gets piled on top of that, so the operating system's running at ring 0. Device drivers at ring 2 and user applications at ring 3. The most sensitive part, the core, is at ring 0. As you get out from there, things are less sensitive. Processes communicate between the rings via system calls. System calls are typically slow, so when an application is making a call to something on the operating system, and the operating system is then referencing device drivers, that whole process is sometimes slow. What typically happens is something just gets loaded in memory and we just access it from the memory space. System calls are slow. Ring model provides that abstraction. Linux and Windows use rings 0 and 3. Hypervisor runs at below ring 0. We'll talk a little bit about hypervisor. Any questions on the ring model? It's theoretical.
I've heard that there's like people call the BIOS ring -2 or -3, and the vulnerabilities that were
Spectre and Meltdown.
Yeah.
Yeah. Yeah. But you typically don't access, because Spectre and Meltdown didn't run in the BIOS. Spectre and Meltdown were running.
I was actually thinking the one that came out. It was only on the business. The vPro.
Okay. Yeah, I suppose you could refer to the BIOS as ring -2. I've never done that, but you could. Because even if when a system's running, you're not accessing the BIOS. You can access the BIOS from the operating system through the kernel, by doing a BIOS flash or something like that, but I don't know.
Repeat the question as we go forward. But.
It was a difficult question that I don't feel like repeating. The question was, some people refer to the BIOS as being ring -2, potentially. And there were some vulnerabilities pre-Spectre and Meltdown that I think compromised potential in the vPro technology or something. Not necessary for the test, certainly outside of the realm for the test, but interesting nonetheless. Here's a conceptual view of the ring model. It's not that, this is pretty easy to memorize, I think. Ring 0 is the most privileged. That's where the kernel operates, and as you go out, you get less privilege. Open and closed systems. For those who don't know what open and closed systems are, you'll need to know this for the test too. An open system is one that has an open architecture, meaning like the or like the x86 systems are all open architecture. Anybody can create, drivers for them. Anybody can create hardware for those systems, and make, so you see a ton of different configurations. Whereas a closed system, the architecture is closed. It's one or a few manufacturers that can actually make parts and pieces for those systems. Apple is probably the most classic closed architecture system. All proprietary. Apple has opened up from what it used to be. Apple used to be super closed. Right? Nobody made anything for apples except for apples. But now other companies can make, lightning connector type devices and other stuff. Belkin's making stuff, everybody. But anyway, traditional sense, open and closed systems, knowing the difference between those two. Now, there's always a debate too. Well, which is more secure? There's no this is more secure than the other, and that wouldn't be on the test anyway. Usually, it's the implementation. It's not so much the hardware that's usually the insecure part. It's the people using the hardware. Right? Attackers are business people. They're in it for the money. They want the greatest return on their investment, and it's always people. So when it comes to like whether an open system is more secure than a closed system, you could debate that all day long. Just like you could debate Windows versus Linux, which people have been debating since forever. Right? Especially those old Unix guys, the guys that used to have the beards and the ponytails, and hadn't seen the light of day for decades. Windows, so insecure. What's that?
Still very much alive.
Oh yeah, they are alive. Yeah, you just don't see them as much as you used to, though. So system units and motherboards, knowing what a system unit is and a motherboard. So a system unit is the case and everything in it. The motherboard is just the flat circuit board that everything connects to, that makes everything work. The king of the motherboard, everything sort of runs through the central processing unit, the CPU. But we've also got memory slots, firmware, peripheral, you name it. There's all kinds of different motherboards. Knowing the difference between system unit and motherboard is what's important for the test. If you want to get into hardware, then deeper than that, A+ or something, just tear stuff apart. That's how I used to learn that stuff way back when. You just take stuff apart and break it. So your computer bus, you'll need to know this too. So computer bus is just a circuit. It's just a way to get information or communication from one place to another on the motherboard. That would be a bus. Buses end, kind of the central terminal. The grand central station would be the CPU. Things either run through the north bridge or the south bridge. The north bridge is faster. It's closer to the CPU. Things like memory connect to the north bridge. Things like peripherals and external devices and things like that connect through the south bridge. So I/O devices all go through the south bridge. That's a good diagram there for understanding how north and south work and where they connect to the CPU. North bridge, also called the memory controller hub or MCH. There's all that information about that. Things that are directly connected or closer to the CPU will always be faster. South bridge is that I/O controller controlling all those I/O devices. For those of you who haven't seen a central processing unit, that's what a CPU looks like. Right? There's an i7 chip there. If anybody's never taken a chip out, there's all the little pins that sit down, and then you chunk it down, whatever. That's a processor. There's different types of processors too, right? Just like anything else. But in the general sense, that's what a processor looks like. You don't need to know this for the exam. A 2.4 gigahertz, that actually means 2.4 billion cycles per second. A cycle is a 4-step process to get through a cycle. It's pretty impressive, really, when you think about how fast computers work. My CPU, this one, is about 200 gigahertz. So I'm kicking the crap out of computers right now. No, you got to think about it. I wonder if anybody's ever done that, like figured out what the human brain is kind of estimated. That's got to be Googled somewhere.
So there's what's it called? It's on NPR every once in a while. Shoot. But anyways, they did a whole thing about how fast is your brain. Yeah, it's actually pretty slow.
Really?
Yeah. Science Friday? Yeah, it was on Science Friday, but it was just like a show.
So the human brain is slow?
Yeah, like really slow. But why it doesn't seem that way is because of our perspective. Like think about a fly. How does a fly get faster than you as well? Because they think faster than us.
Flies think faster than us?
Yeah, that's why they can see you coming faster.
Like
you're super slow to them. You're like, well, they're like,
Not so much thinking as the nerve system is short.
Right.
Okay.
So because it's so long. And
so a fly is truly a reduced instruction set computing system.
Right.
Super good and fast at this one thing, whereas we're more general computing and can do a bunch of other things, but slow.
Right. But they did actually map it out to actual this is how long it takes to do just this one thing. So it's kind of interesting.
Yeah, it is interesting. Again, there's CPU. Two things on the CPU: the ALU and the control unit. So the ALU does all the math, which is easy because if you know ALU, it's the arithmetic, right? That's math. It does all the math, all the calculations. The controller unit is kind of like the traffic cop for the CPU. It controls what comes and what goes and how it comes and goes. It's its job. This is a cycle, so you can imagine 2.4 billion times per second going through this same cycle. Fetch instruction, decode instruction, execute instruction, and then write instruction. That's a cycle. One CPU, one clock cycle, 2.4 billion times a second. Those things happen in a computer, or what it's capable of. It may not be doing it that fast. So more stuff to memorize. That 4-step process. We've also got things called pipelining. So pipelining, there's serial computing, which would mean I'd have to go through one cycle before I start another cycle. Pipelining means as I, fetch one and then go into the decode, I'm fetching the next one. So I'm actually able to run 4 cycles, concurrently, sort of, right? They're pipelined. I mean, at any one time, there's 4 cycles that are happening at one time in a CPU that's doing pipelining. Does that make sense? That diagram is communicates it better than I am right now. You can see in non-pipelined, it's serial. I have to complete one complete instruction, one complete cycle before I start another cycle. In pipelining, I fetch, and then it goes into decode while I'm fetching the next instruction. While instruction 1 goes into execute, instruction 2 is now in decode, and another instruction starts in fetch, right? And that would be that pipelining.
If you're familiar with project management, that means non-pipeline is waterfall, pipeline is agile.
Yep.
Yeah.
Yep. Yeah. And in project management, now are they teaching waterfall or modified waterfall? Like you can iterative, right?
They're leaning more towards the iterative and the agile.
Okay. Because that traditional waterfall where I can't go back and fix what I did before, that doesn't, in practice, that doesn't work because nobody gets it right. But, and we'll get to that when we talk about software development too. We'll talk about agile framework. We'll talk about sashimi. We'll talk about, Scrum, all that stuff.
Scrum is part of that.
Yeah. Yep. But different than agile. I mean, Scrum is a part of agile, but not agile.
Like 2-week sprint.
Can be. 2 weeks can be you can do a 1-week sprint if you want.
So do you want to go back real quick?
Not
Yeah.
really.
So how is this actually how do we see this?
See it?
Yeah, so we're not really going to see it because it's moving fast, but what I mean is it's so that example of you double click the MP3 and then it plays, right? So how is this functioning, whether it's pipeline or not? How do we?
There are thousands of instructions that are taking place when you double click an MP3 file.
Well, right, so that's an example of pipeline, right? Or
Your processor is pipelining, right? Yep. Yep, absolutely. Yeah. Right, interrupts. So an interrupt happens typically hardware interrupts, so the most common type of interrupt, but it stops the CPU from processing so that it can process this interrupt. You want to minimize the number of interrupts because as a processor is continuing to do its thing, it has to stop what it's doing, save it to a register, and then process the interrupt and then fetch back again from the register and then continue. So every time you have interrupts, it slows down the computing time. Interrupts typically are hardware related. That's the most common type of interrupt. Process, so these things we'll need to remember too, the difference between a process and a thread. A process contains threads unless it's a heavyweight process. A heavyweight process just means that it's also called a task, but there's no real threads. They all share memory if there are threads in a heavyweight process. So a process, an executable program, and its data loaded and running in memory, that's a process. And you can see it in Windows, Task Manager, and you can see all your processes. That's fairly easy. Threads, you'll need to use something different. Hello, my brain's not working. I think I'm in utility. PS Tools, it's part of PS Tools. What's the?
Process Explorer?
Yeah. Yep, and then I can see actual threads with Process Explorer. So if you ever wanted to play with it, you can, certainly do that yourself. Processes and threads. Threads are individual instructions. A process or a thread that's been left to hang. So the parent process has been killed and the thread is still running. That's a zombie process. You don't have to get into too much detail unless you're, writing code, but that's what those work.
got a good question online with regard to pipeline versus non-pipeline, similar to hyper-threading.
Yeah. Yep, similar to hyper-threading, I believe. I haven't used that word hyper-threading in like a century. Seems like, so I think so. Any questions on this? Processes and threads, the difference between a lightweight process and a heavyweight process, and knowing what a zombie process is. Those are all important things for you to know for the exam. Bless you.
What would be an example of the zombie process? Where would it happen where a parent is terminated but the thread is continuing?
Chrome.
Yeah. Yeah, that happens. Java, poorly written Java apps are very notorious for.
I disagree. That implies they're well-written Java apps.
That's true. That's true. That's true. Every Java app, yeah. And you can notice these things, like in Java, you can certainly notice it because you'll have what we call memory leak. Right? You keep getting these spawn processes that keep taking memory, and then I'm not running anything yet. I'm running out of memory. A poorly written Java app would be. That's why you'd notice it. Zombie processes. A lot of times you won't even know it because they will time out eventually. Most application developers, or you'll reboot or something and it'll be gone. Multitasking, multiprocessing, multiprogramming, and multi-threading. These will all be things that that you'll need to know for the exam. So anytime you see the word task, that's a heavyweight process. So multitasking would be heavyweight processes are running simultaneously on one CPU. The simultaneous would be probably through, going back to our pipelining would be using pipelining as well. Multiprocessing, multiple processes on multiple CPUs. So multiprocessing, think multiprocessor. That's multiprocessing. Symmetric and asymmetric multiprocessing, it's just what I can run on those processors. Symmetric multiprocessing is one operating system is managing multiple processors, whereas asymmetric is each operating system is running a processor. That's the only difference between asymmetric and symmetric multiprocessing. Multiprocessing used to be really, really familiar, or not familiar, popular, but it's just not that popular anymore. Most people are just running single processor systems, or they're using shared computing. Multiprogramming, multiple programs running on the same CPU. Multi-threading, multiple threads running on the same CPU. So in most cases, all of us on just normal computers are running multitasking, multiprogramming, and multi-threading operating systems. Most of us are not running multiprocessing systems, right? Does that make sense? Remember multitasking, task, heavyweight process, multiprocessing, multiple processors, multiple programming, multiple programs, and multi-threading, multiple lightweight processes. Threads are lightweight processes, right? Makes sense? It's just all in the word. So those are easy to memorize. Watchdog timers. A watchdog timer is used, when a computer system crashes, and a watchdog timer is used to bring the system back up again. So recovering a system from rebooting or critical system. You've got complex. Did we talk about this yet? Complex and reduced instruction set computing. Most of us, the commercial systems that we run and go buy at Best Buy are complex instruction set, meaning they're not specifically designed to run specific processes. They're general purpose computers. Reduced instruction set computers are ones that are specifically built to run a reduced set of things. Like even in my iPhone, this A10 processor is a reduced instruction set computer. It doesn't run all sorts of applications. It really is specifically designed for a mobile computer. Other reduced instruction set computers, what you have in your car is a reduced instruction set computer. What you have in a lot of IoT devices are reduced instruction set computers. Does that make sense? So knowing the difference between complex and reduced instruction set computer systems. Also, and just because a reduced instruction set computers don't have to be small, there are very large reduced instruction set computers that are used for high computational, like climate modeling and stuff like that. What's that?
A6, like
A6. There you go. Perfect one. Yeah, bigger computers but they're very math heavy, very engineering heavy.
Would there be a connection between the open and the closed hardware? Like,
I would say
reduced be
most
more of a
reduced
closed-
instruction set computers are probably closed systems.
Yeah.
Yeah, but it's not exclusive. Addressing modes for CPU, so this is memory addressing. You'll need to remember there's really only direct and indirect. It's whether or not I'm accessing it from the register or I'm accessing it from secondary memory. So direct, and the difference between direct and indirect is direct is a reference to a specific address in memory, whereas indirect is a reference to another location within memory. So it's a reference to another reference to a location in memory, right? That's the difference between direct and indirect addressing. Whether I'm doing it in RAM or SRAM or I'm doing it on a register would determine whether it's just direct or register indirect. You see what I'm saying? So just knowing the addressing modes, knowing how memory addressing works is outside of the scope of the exam, so you don't have to get into that. Just knowing the addressing types is good enough, for now. Okay? Because you could seriously spend a lot of time in memory addressing if you wanted to. This is from the book, so you can see the direct addressing, direct, and then a reference to another location in memory would be that indirect, whether it's in the register or in memory. This is the difference.
Okay, so if it's an unregistered one, it'd be like your temporary download folder, and your registered one would be where you actually saved it somewhere.
No. Now, both of those would probably be direct non-register.
Non-registered.
The things that happen in the register are minutia that you don't know. You don't see it.
So how would you tell the difference?
Well, they would just reference it on the exam. You won't know the difference unless you actually program at that level. You know what I mean? What's stored in your cache or, other places would all be, it's either written to disk, so it's truly secondary memory, it's been swapped, or it's in your normal memory addressing. It wouldn't probably be in the register.
Indirect, pretty much normal now, because security content.
What's that?
Indirect to normal now, since there's security content.
Oh, that's security. Yeah, I think there's security terms with both. Yeah, because all you have to do is change pointers, right? Whether it's direct or indirect. I think it's easier probably if you're, like the most common type of attack here is a buffer overflow attack where we call it smash the stack, and then, it spills over to the next memory address, and so then that's where you insert your code to run. So when the program fetches the next memory, it's going to run your code instead of the code it was supposed to. I think that's easier to do probably in direct than indirect. So memory protection, things that I can do not I can do, but things that are built into programs that developers would do to protect memory. Obviously, we want to protect. We want programs, processes, threads to sort of stay in their lane. Right? I don't want a process or a thread from one application accessing space of another application, because what can happen is one application has privileged access and one doesn't. They're both running on a server, let's say, and I can jump into the other address space. I could potentially access code or access information at another privilege level that I don't, you see what I'm saying? So the process isolation, keeping processes kind of in their lane, is one way that we can protect that from happening. Object encapsulation, if you're an application developer, you'll understand what encapsulation is. We'll talk a little bit more about encapsulation later, so it may not make a lot of sense here. But encapsulation is instructions that are happening here are encapsulated and in code. Objects are reusable. So what happens here is hidden from what happens here. So I can hide, lower level things over here potentially, and then just use system calls through coupling. That's what object encapsulation is. We'll get deeper into object encapsulation when we talk about some software development stuff. Time multiplexing, this is, multiple processes get a specific amount of time with the processor, and then they're written to disk and then, or written to another place in memory, and then the next one gets its time. So time multiplexing is all just based on slices of time. Now the ALU or CU, which one of those would control time multiplexing in the processor? The control unit, right? The CU, right? The arithmetic logic unit would actually be doing the math. So that's just a quick application of where this plays. Hardware segmentation, this is another way I could do memory protection, complete segmentation and isolation of hardware. So if I have one computer system over here and another computer system over here, this one runs this application, this one runs this application, chances are pretty good that the memory that's physically segregated, it's not going to be shared by the two applications. That would certainly work. That's, as a security guy, that's my favorite. Right? I like highly sensitive systems only doing highly sensitive things. I don't want less sensitive things happening. You know what I mean? I like to keep hardware separated whenever possible. Yeah, separate servers. That's the best way for memory protection. And I can control that as a security guy. I can't control how applications are written very well. I can do some pen testing, or hire somebody to do some pen testing to make sure that the application's running that way, but at the end of the day, I don't have a lot of control over that, but I can control hardware segmentation. Did you have a question?
Well, wouldn't that be really expensive though, to have a separate server?
If it's a highly critical system, I can probably justify the expense.
Sounds a big deal, virtualization.
Right.
And virtualization, right? But even the best cases, the best advice and best practice, even from places like VMware and Microsoft, is to not run different classified systems on one hypervisor. So even they're saying to run different virtual, physical machines for those virtual machines. There's only 2 attacks that I know of where you can actually attack the hypervisor and get from one operating system into another. And neither one of those are practical, so I don't know if I go through this. I think I just stick with the virtual, but the best practice is that you use different hardware.
Don't have Visual Studio running.
What's that?
At the very least, don't have Visual Studio running.
Do not have Visual Studio running on your domain controllers. We don't like development tools or compilers on servers. Virtual machine or virtual memory. Virtual memory is just swapping, right? There's swapping to secondary storage, whether it be a hard drive, whether it be an SSD, whether it be even flash drives can be secondary memory. But if you're doing virtual address mapping, that way, that's another way potentially you could protect memory. That's the same thing with swapping and paging. Virtual memory and swapping and paging are somewhat synonymous, but slightly different. Swapping and paging actually just uses that virtual memory. And swapping and paging is slower because I've gotten further out from the CPU for one, plus I'm dependent upon, the bus speed, the USB speed maybe, or, whatever the person, or even if it's a hard drive, a lot of times I'm limited by how fast that hard drive spins. That was the biggest thing for laptops for the longest time was, you were limited to 7,200 RPM hard drives. And every time anything would swap, and Windows is loves swapping, right? So Windows would run slow on on laptops compared to, a 10,000 plus, spin drive on a desktop. But now everything's SSD, so swapping isn't as big a deal. But that's one way I could protect memory is just swap it out to disk. All right, any questions on all that? Is that exciting? I'm pretty excited that I'm done with it. But it's a lot of that just memorization. I'm not much of a hardware guy anymore. Way back when I used to be. Now I just don't do that work anymore. So a lot of it for me too is going back and what the hell? Oh yeah, now I remember how some of that works. BIOS stands for Basic Input Output System. BIOS is ROM or EEPROM or EEPROM on a motherboard, and its job is basically to get the system up and running, right? Contains code and firmware that's executed when the PC is powered on. First thing it does is run that post test. It used to be you'd have to watch it do that post test. Now, there's fast post, so a lot of times you don't even see it. But what post is doing is it's checking memory, checking to make sure all the components that are required for the system to run are there, and then it looks on the first sector of the first disk for the kernel. Right? It's looking for that boot drive. Kernel loads and executes into the OS. Now, different kernels do different things. Load system drivers, allow the display to work, better, whatever else. Is that in your way? Oh, there's not much I can do about that.
I got the list of the building, so.
You can pull the blackouts down. Do you know how?
You're assuming I know how to do that?
There's a thingy that just says shade.
That's not right. Shade controls?
Yep, that's it. There you go.
It's about ready to get real in here. We should get some mood lighting, maybe some candles. All right. Any questions on post or BIOS or kernel, boot sector, any of that stuff? That one goes longer than the other ones. All right. This is a good graphic, I think. So the PC is turned on, the BIOS initiates. So just memorize what happens with this graphic. I would set in the BIOS what my active partition is or where my active hard drive is and all that other stuff. And that's where it's going to look for that kernel. It's going to look for it in the boot sector. 512 more bytes located on the first sector of the drive. That's the default of where your master boot record resides. And the master boot record would be the pointer to the kernel. Read once, write once, read many. This is slow archival type storage. This is not something that I would regularly recall back from the array. This is more like library type stuff, archival type stuff would go on worm drives. Not that kind of worm storage, that kind of worm storage. DVDs, CDs are common for worm storage, not RWs. That's read write, right? Easy enough. High integrity information, usually longer retention periods for worm storage. TPM, there's modules on some hard drives that have the trusted computer platform module. Like if what's the Microsoft BitLocker. So if I have a TPM, then I don't need to have that USB device or know my big long recovery key and all that other stuff. So TPM. Now TPM, it's hard to find it. It used to be a little easier. I don't know what systems run TPM chips and which ones don't anymore. I know that Lenovo has a very few systems that are actually running TPMs now, and I don't know why they've done that. But TPM allows us to do things like some security components, like encryption is the biggest one. Allows it to run in hardware, which makes it faster, right? If I run it in software, I'm going to lose probably 3 to 5% CPU as my computer is running, whereas if I offload that to hardware, into the TPM chip, it's much faster. The most common method, and also you can't bypass the TPM. So there's this thing, when I encrypt a hard drive, the boot sector needs to load what we call pre-boot authentication, or TPM can enforce that too. Because if I don't have pre-boot authentication, I can just bypass. In Windows, it's the GINA. It's that's what displays your login page. I can bypass that, change the password, and still get into your hard drive. So pre-boot authentication is really important with full disk encryption, or having a TPM chip. Hardware-based encryption, fast. We love hardware-based encryption. Hardware encryption is always a mathematical issue. It's always a CPU issue, more than anything else. Any questions on TPM?
Online question was regarding the boot process. Is that going to come up on the exam?
The boot process?
Yeah,
yes.
UEFI, boot process.
Oh, the UEFI? No, that will not be on the exam. Department of Defense, their TPM stuff, that's just a tidbit. You don't need to memorize that. Knowing what TPM does and how it works is, I think, good enough. Data execution prevention and address space layout randomization. This will be more things for you to memorize for the exam. We'll get more into this when we talk about buffer overflow attacks. This is really where this comes into play more than anything else. Data execution prevention, you can think of as running like application whitelisting is one way that you could implement data execution prevention. And that's actually, application whitelisting also happens to be one of the most effective ways to protect yourself from ransomware, but that would be using data execution prevention. Address space layout optimization or randomization, not something that we really implement that I know of much. Maybe Cylance or something is using something like that, but that's what that is. Here's our kernel, 2 types of kernels, monolithic kernel and the microkernel. The microkernel is what Windows uses. So that means I can add new functions, new features, and they're just essentially modular. They plug into the kernel. Whereas a monolithic kernel, every time I add a new feature, I have to recompile, right? The old Linux, not so much Linux anymore, more the Unix systems would require, a lot of those are running monolithic kernels, so I have to recompile the kernel every time I add something. Like I would add a new display driver, recompile the kernel. You don't need to do that, with Windows. Windows is a microkernel. The kernel is the heart. It runs everything. Everything runs through the kernel in one way or another. Part of the kernel is the reference monitor. The reference monitor mediates all accesses, everything between subjects and objects. That's the reference monitor's job. And there's a good graphic to explain it. So going back to that fundamental thing that we talked about with subjects and objects, the reference monitor enforces that. It enforces that through what's called the security policy. Cannot be bypassed, or it's not supposed to be. Right? Anything, I think, some level can probably be bypassed, but it's never supposed to be bypassed. So if the kernel is insecure at the core, then you'll be able to bypass it potentially. File permissions, we've all seen this before. This is Linux file permissions. If you've not used a Linux system, ls-la would give you what you're seeing on the screen here. This would be for the etc directory. And then you can see owner, group, and world. So the owner of this directory has these permissions. It's either read, write, execute. Read, write, execute. The group permissions and the world permissions, that's it. The D's on the far left just means it's a directory. You can probably see it in a different color in your own system. Linux, you probably should run a Linux system if you've never run one before. You can just run a VM on your own computer and load up a Linux system. You can load up Kali if you want to see what a Linux system is. Just Google Kali. You'll find a bootable drive and you can just load it up and run it. So Linux is good because you'll run into that. And there's a lot of cool tools that run on Linux that you won't be able to get on Windows and vice versa. Windows permissions, right click, select properties, and there's your permissions somewhere. In their NTFS permissions, so NTFS is NT file system going way back to the 3.5-ish days, still the same base file system in use today. Read, write, read, execute, modify, full control. You probably monkeyed with permissions there before. There's a screenshot of what that looks like. Virtualization. So I've got 2 types showing here of virtualization, but it adds another layer. The operating system runs on top of the virtualization. In some cases, the operating system will host the virtualization, so I can run. There's a hypervisor that runs within Windows, like a lot of our desktop. I'm trying to think of Oracle's got one that I use a lot. VirtualBox. There you go. That would be this kind. The one over here on the right, that would be where I can run multiple operating systems within an operating system, whereas like VMware ESX would be a hypervisor, and I could load a bunch of operating systems on top of it. So multiple guest systems can run on one physical host, transparent or full virtualization, running stock operating systems. Paravirtualization means that the operating system itself has been modified to support virtualization. Most of what we're running, all of us, is transparent or full virtualization. Hypervisor, type 1 and type 2. Type 1 is like the VMware ESX. Type 2 would be like the VirtualBox or VMware Workstation, where I've got the operating system running software that contains the hypervisor that then can run another operating system. That's a type 2. The type 1, typically running servers to be ESX host, something like that. And the hypervisor is just the software that controls that, right? Now, in the case of the one on the left, that would be more of a ring -1 type configuration, where I've got the type 1 virtualization. The type 2 virtualization would be really running more ring 3, right? Because the kernel is running at ring 1 for the host operating system, and then I'm running an application, so it's running on ring 3, and it's virtualizing really another ring 0, ring 3, if you're interested. So benefits, obviously the virtualization, distributed computing, lower cost, lower footprint, lower power, lower heat. We used to have, pancake boxes filling entire racks, and you can never keep them cool. Those are all big benefits to virtualization. Security issues, more complex. Complexity is the enemy of security. So the more complex I make things, that doesn't mean that I know how to exploit it. I just know that it's less secure because it's more complex, right? It's just the theory. Easy to bring up new systems without proper checks and balances. It's easy to spin up VMs. We ask people to spin up VMs for us all the time when we're doing pen testing, and they just, spin it up. So it is very easy to bring up new systems. Very rare to have issues with hypervisors. There are 2 attacks that I know of, and I can't even remember the names of them. I used to talk about it a few years ago, a few classes ago, but none of them have ever been successfully done in the wild. It's been in a closed environment. I don't know of any attacks against hypervisors, current hypervisors, that allow you to jump from one operating system into another. So, but just because I don't know about it doesn't mean it doesn't exist either. Have you guys heard of any? Spectrum Meltdown theoretically could, yeah, but I've never seen that exploited. Supposedly there's exploit code for it, but I've never seen anybody attack it. Yeah, Spectrum Meltdown supposedly, theoretically, would be able to attack that. Cloud computing. So cloud computing, now everybody's kind of moving to the cloud. Cloud computing, when it first came out, was like kind of funny because it was really just networking. And we always thought of like a colo is cloud computing. We just called it a colo. An application like Salesforce, right? We wouldn't call that software as a service. We just call it Salesforce. But now, software as a service, platform as a service, infrastructure as a service, all kinds of different cloud services, knowing in general what the difference is. So like Salesforce it's just the software. The only thing I interface with as a consumer is just the software. That's software as a service. Platform as a service is taking it kind of to the next level. Now I've got maybe access to the database, maybe I have access to the operating system, maybe access to other things. Infrastructure as a service is really just the base infrastructure. You could tack on virtual machines or virtual systems as infrastructure as a service, but it kind of branches between infrastructure and platform as a service. For me, it just confuses everything. I just call Salesforce, right? But it's software as a service. We get customers that are like, hey, we want to go from IaaS to PaaS. What do you think? I'm like, let me look up what IaaS is again and look up what PaaS is again, and I can tell you what I think, right? Because there's just so many buzzwords. But anyway, infrastructure as a service, virtual machines, servers, storage, load balancers, network, truly infrastructure. Platform as a service is assume that I've got kind of an operating system set up. It's all the other things that go on top of it. And then software as a service just takes it up another notch, another level. Cloud clients, all kinds of different cloud clients, like Office 365. How many people are using Office 365? When that first came out, man, there was so much resistance to it because, everybody just loved their Exchange servers and all that. But then you started seeing some of the enterprise clients kind of going out to Office 365. Now I can't even imagine why we would ever run our own Exchange server again, right? Exchange servers. Well, you won't get, that's okay. Everybody's got their own. You do want to get rid of yours. Yeah. I mean, Office 365 for us, we're 50 some odd employees. The last thing I want to do is hire a whole IT team just to manage my IT or manage my Exchange server.
Just be aware that if you're using Office 365, that's PCI compliant.
So no PCI compliance. He's a QSA. He says so.
No.
So just don't have to.
AW or Azure, they have portions of that are PCI compliant, but Office 365 in the cloud, Microsoft says they will never be PCI compliant.
But then that brings up another thing. Why would I ever email
Yeah.
Exactly.
credit card information?
Exactly.
Why would you
But
ever-
just scope it out of your PCI, your cardholder data environment. You should be okay.
So,
Is that what you guys advise? Just
but you've
CDE
gotta,
stops here.
you've gotta work with your clients because a lot of clients still get emails with credit card numbers. So,
Oh.
again,
Well, I don't know. I never make that compliant anyway. Yeah, I agree. Other things, grid computing. So grid computing is really just shared computing resources to complete a task together. It's truly multi-processing to another level, right? It's now because multi-processing is multi-processors. Now we're talking multi-computers. You know, that's grid computing. BOINC, anybody ever heard of BOINC? A lot of gigaflops. Gigaflops is a lot of flops. A lot of, I don't even know how many, that'd be a lot of zeros. I got it right there. 165 to the 10 to the 15th flops, right? And then take that to instructions. I mean, it's some serious computing power. They use that, like Hadoop is sort of like a good computing too. Anybody ever use Hadoop? Hadoop is shared computing resources. Oftentimes used more for data analytics or storage more than, true processing power. But BOINC, yeah, there's lots of different ones. There's SETI. You can make your computer part of SETI if you want to be part of the grid computing movement. Looking for aliens. Peer-to-peer, we don't see, peer-to-peer blew up for a while and then it sort of died out. I mean, we just don't see a lot of peer-to-peer, but Tor. What? No, Tor wouldn't be peer-to-peer. Tor would be just a separate network, I think. Peer-to-peer is truly, there's no central kind of location. All computers are kind of sharing amongst each other, so it's like drawing lines with everybody would be a peer-to-peer. Bitcoin, yeah, if you're involved in the mining, if you're a mining system. Who does?
Windows 10 for sharing.
Windows 10 and share, okay.
I think it's doable to opt into it.
But what was the big music one that everybody got? Napster. I was gonna say that I got in trouble for, but everybody got in trouble for. Right? Sharing your MP3 files. And then what, seriously, my brain is like toast. What's the other one? No, not LimeWire. No, not for so much for music, but I would. Torrents. There you go. Did you say what you said? Torrents, or did you say Tor?
Tor.
Okay, Tor different. Onion Network. Torrents different. What?
They're all on your slides.
I have them on my slides. There you go. Just refer to the slides. Quality slides. Whoever put these together, just look at those. BitTorrent. Yeah, BitTorrent. Used to monkey around with a lot of that stuff anymore, but now, it seems like peer-to-peer has sort of died a little bit. Yeah, anyway, but knowing what peer-to-peer is, peer-to-peer truly, there's no central point. And you brought up a blockchain is a good example, I think, of kind of peer-to-peer for a specific purpose. Yeah, anyway, so we don't have to go into Bitcoin and cryptocurrency so much here, but that is kind of a big thing now, and cryptojacking is kind of a big thing now. Loading malware onto your computer so that I can use your computer to mine for me and I can take the money. Right?
They've been doing that to organizations that have lots of servers and stuff. They
Oh yeah.
sneak it into a
The guy that did it in Finland that compromised 600 servers in what the hell was he? Iceland. 600 servers in Iceland walked out of jail. They put him in a minimum security prison and he just walked out. Flew home. Like son of a really? No justice in the world. Thin clients, diskless workstations. It's funny how the world kind of works because we started here. We started with mainframes, right, with dumb terminals, and we blew up into this, client-server environment where everything was distributed computing. Now things kind of coming back a little bit. They're collapsing back on themselves, and that's what thin clients, diskless workstations, and thin client applications. The only difference between a thin client and a thin client application is the application itself is the thin client. Typically we would be running from like a browser or some thin client application, and then everything kind of runs in that thin client application. No data is actually transferred to the endpoint. you have those central servers. Everything runs on the server, which makes the attack footprint a lot smaller, a lot less vulnerabilities for attackers to attack. In a diskless workstation, it's just, there's nothing there on the workstation. There's no disk there. When it boots up, it uses boot P or, to find how it's going to load, what operating system it's going to load. There's no control at the endpoint for that. And it uses the same, similar to DHCP, boot P is.
Can there be anything on the new test with VDI and DAS?
No.
So,
Repeat the question.
Oh, will there be anything on the test around VDI and DAS? And the answer is no, probably not. It's not updated enough.
so if somebody comes in, they go to whatever workstation they're working on, and they have to log into Citrix to get to all the work that they're gonna do. Is that a thin client or is that a thin client application?
Thin client application, probably.
Because they have to go through Citrix to get to their actual.
Yeah, because they're already into the operating system, and then they're logging into Citrix from the operating system. That would be a thin client application.
Right. They don't have to actually log in, they just have to log into Citrix, right? They don't have to log into the computer itself.
They
The
don't,
workstation itself,
potentially, you could set it up that way. Sure.
so it would be an application kind of thing. So how would you know the difference? So what would then be a thin client? Where would you use a thin client like that? So if I'm dumbing this so that all they have to do, the only thing.
A thin client would be a very specialized system, and it would load just a very limited desktop environment, and then it would work a lot the same way as the thin client application, but a thin client application typically runs on a full, like it would run on my laptop. It runs on a fully functional, not isolated kind of computer.
So.
VDI, right?
Yes.
Okay.
Yep. But I don't think you have to get that specific for the test. You don't have to worry that much about it.
So what is it when I create another profile that only allows you to run one or two applications, you can see everything else?
Probably be more of a VDI. Yep. Internet of Things. You don't have to go a lot here. This is just like pain in the ass.
Showdown.
Yeah, Shodan's a good tool. So Shodan, SHODAN, is a good place to find your IoT devices and other things. Good place to find RDP systems hanging out there. IoT and RDP are the two things that we find are compromised most quickly on the internet. So, my refrigerator orders milk for me when I'm out of milk, right? That's an IoT device. My camera, my baby monitor, my lights that I can control, my garage door opener I can control from my computer. I mean, all those things are IoT devices, but they're also IoT devices for heating and control, HVAC systems. There's IoT devices for water control systems. I mean, you're seeing utility companies now leveraging IoT. It's just getting crazy. So it is a security nightmare because most of those systems are not updatable, right? And most of those systems are not configured outside of what the default usernames and passwords are and other default settings that anybody can go and find the manual and see what it is and log in and compromise the system. So it's just...
Don't get one of those internet connected locks for your door so that Amazon can deliver their stuff inside your house.
I'm not telling you what risks to accept. Like I said, I don't make risk decisions for others. I advise them on the risk and let them make the decision.
You may want to repeat that online.
Don't buy the internet-controlled lock that allows Amazon to come deliver things inside my house. Yeah, they can leave it on the doorstep. For me.
What do you think about other IoT devices, though? Like, would you connect an Alexa in your house?
In my house? No. My house, I'm different. My house is the one place that I get away from all this crap. My house is the one place where I can just veg out, watch TV. I'm not connected to crap. I do have internet access at home, but beyond that, that's about it. So, yeah, I just like.
They just put a 2x4 brace on.
What's that?
They 2x4 brace on and call them.
Pretty much. Yeah. Right. Actually, I have concealed carry, so I got guns and stuff too. Yeah, I don't like. We deal with this stuff all day long. When do I get a break? So I just don't connect things to my house. I can go to the go to the garage door myself and push the button. I can go to the store and order milk when we're out of milk. You know, I mean, there's just all those things I can do. I can push a few extra buttons on my remote control to find the TV show I want to watch. That's just me.
But what if, like, your kids were at the house and they left everything on, and now you're at the cabin? Are you going to drive all the way back to do it?
I'll pay the extra $1 or $2 that it's going to cost me to wait till I get home, or I'd call a neighbor. Or I probably wouldn't even know. I'd just get home and be like, oh, somebody left the damn light on. And then I'd scold my kid, take away their phone. So emanations, you know, this starts to get a little spy-ish, right? A little spy, you know, the thing you need to remember about emanations is Tempest. Tempest is a government-controlled standard. We don't know the full standard. Really, Faraday cages, things like that to prevent emanations from getting outside. So, you know, theoretically and probably proven, you know, you can, based on the electrical impulses that are happening on my computer right now, you could be sitting on the other side of the wall, detect those electrical impulses and tell what the computer is doing. You could infer what the computer is doing, what it's accessing and things like that. Tempest is meant to protect against that. Shielding standards, many of them are classified. It is a government standard. If you want to know more about Tempest, you can certainly Google it. But for the test, what you need to know is just Tempest is to prevent emanations, and it's a government standard. Covert channels, anything that's a covert channel, you think of covert, it's bypassing or it's going around the way the system was designed. That's a covert channel. It bypasses policy. Two primary covert channels are storage channels and timing channels. Timing channels are typically an inference attack. So if I know it takes X amount of time to do recall this kind of file and X amount of time to get this kind of file, and yours took this amount of time, I can infer that maybe it's this type of file. Stuff like that happens with timing channel attacks. Storage channel attacks are typically poor implementations of operating systems or poor configurations or something where we're both using the system. You've got top secret clearance, I've got secret but unclassified clearance, and we both I can access the swap directory, for instance. I can access the paging file because of a poor configuration. So as you're using your application and your application's writing to that paging file, if I can access that paging file, that's a covert channel, storage covert channel, stuff like that, right? Two types of primarily covert channels.
Does it like include sniffers and things?
No. Sniffer is just a punch you in the face. No, I don't. No, we don't like sniffers, but not here. Sniffer is potentially a covert channel because it bypasses my policy of what I've implemented onto the network, but not here. Sniffers we don't like because they're very difficult typically to find. You know, we have to find those through typically electrical signals and stuff like that, and maybe, you know, some traffic shaping monitoring things because they sit in promiscuous mode. They don't put anything on my network.
So they're more physical than.
These are two covert channels, storage and timing. This is related to a computer system, not the network. Backdoors and maintenance hooks. So backdoors are typically, it's a backdoor into the system. It bypasses the typical front door user authentication process. It's another way into the system, bypassing security checks. Backdoors so the difference between backdoors and maintenance hooks, they work similarly. A backdoor is malicious. A maintenance hook was put there on purpose by the developers to help them develop the code quicker. Sometimes they forget to take it out, right? So we would, you know, that's why QA and DevOps is so important, is we would try to identify those maintenance hooks before they go into production. But backdoors are planted, typically. You know, the typical attack sequence is identify a vulnerability, compromise the vulnerability, so now I've got a foothold into the system, elevate my privileges to that of an administrator, plant the back door, delete evidence, and come later. There's a pivot in there sometimes. If the system that I've compromised doesn't have anything that I'm really interested in, I'll use then that system that I did compromise as a pivot. So I'll scan. I'll usually upload scan tools, utilities, and then just conduct scans. It's really that way almost every time. A backdoor would be something that I'd plant so I could come back later. That's what attackers use backdoors for. Lots of different kinds of backdoors. There's, remote access Trojans, rats, sometimes they're called. One of the attacks that I was talking about, did I share with this group? Remote access Trojan on the domain controller with an active connection back to the Czech Republic. That's what we found when we responded to an attack over a distribution company, pretty good sized distribution company. They didn't even know about the attack. They didn't even know anything had happened until one of their big customers, it was a B2B kind of business, one of their big customers texted the CIO of this other company who ended up being our client that, hey, we stopped all emails coming from you guys because you guys were phishing us. Like, phishing you? How are we phishing you? And then they decided, well, maybe we should call somebody. So then we started the investigation, and 13 minutes it took to find the remote access Trojan on the domain controller. Once you find that, talk about the core of something being insecure, it's basically start over, right? I mean, Lord knows what you can do when you've got, root access to a domain controller, admin access.
How'd you find it?
Simple scan. Started off with just a simple, let's just kick off, because we didn't know. We started with Q&A, trying to determine kind of what's going on. Figured that this attribution was going to be pretty much a lost cause. We have to contain what's going on. So just a simple Nessus scan, actually. Started off just discovery. What the hell are we working with? What systems are out there? And Nessus has a number of plugins for malicious code. And then it popped up, like, really? So then you go and take a look, and it's there. All right, so malicious code, malware, viruses. So things, viruses and worms. Viruses embed, worms spread. Okay, viruses embed, worms spread. That's a big differentiator. Viruses typically just infect one system, and that's where they stay. If they spread automatically, we would classify that typically as a worm. So viruses and worms. All kinds of different types of viruses, macroviruses, yes, they're still around. Thank you. What was it? Melissa? Is that the first one? Mm-hmm. Or one of the first ones? Melissa, 10, 15, 20 years ago. Still very much in play. Boot sector viruses, that's where I started my career in 1992, was cleaning boot sector viruses off of Windows 3.1 machines. Right? Boot sector viruses aren't nearly as popular as they were then, but they still are around. Stealth viruses, polymorphic viruses, those are the ones that are really difficult. There was a county that I did an incident response for that had the Emotet virus, which is a polymorphic virus, so it changes its form as it goes from system to system trying to evade detection. Those are difficult viruses to respond to. Multi-partite viruses are just, there's different parts to the virus that combine to make up the infection. So those are different types of viruses. This is just more worms. Worms self-propagate. Worms used to be made more for disruption than they were for actual propagation and then something else happening. Now ransomware really is using the same type of, propagation technique where it's self-propagating even outside of, like the way ransomware first started off was ransomware would infect, actually ransomware goes way back to where you used to have to pay the ransom to a P.O. box. Ransomware has been around for a super long time. But ransomware infects one system and then based on what that user has access to, goes out and encrypts things. The ransomware itself doesn't propagate to the other systems and then reinfect. That was a newer kind of thing in the last, let's say, 18, 24 months, that now the ransomware actually propagates and spreads. So it goes a lot faster than it used to. That malicious code itself, wasted resources. That's how most of them were, started, was worms to just waste resources. But now, like Code Red was a pain in the ass. You guys remember Code Red? Anybody? 99, I think, ish. Code Red was this the one that would scan for 1434 open on the internet? People used to have, or 1433, they used to have, people used to leave their databases open on the internet back then. So 1433 was open all over the place, and then this would scan for those 14. Slammer, that's the one. That one was a pain. Code Red took down ISDN lines. I don't know. Anyway, these are old ones that weren't fun back in the day. Trojan. So Trojan's the same way, if you remember or know how the attack on Troy worked. They built this Trojan horse, packed a bunch of soldiers in it, presented this Trojan horse as a gift. And they're like, oh, thank you for this gift. And they brought it into, this is the story anyway, brought it into inside the city walls, and then soldiers came out in the middle of the night, right? Same thing with, it looks like a legitimate application. Oftentimes they come in the form of like a game or something, but they're bad. They do a lot of bad things. Second function, malicious. So the first one looks normal. Maybe an attachment, might be a PDF, might be whatever, looks harmless, and then you execute and it plants something or does something bad. Zeus, CryptoLocker, NetBus, Back Orifice. Yes, it is Back Orifice, if you didn't know. It's Back Office misspelled. That was the name of the malware. Androids are, I think, 96% of all malicious software for mobile devices is written for Androids. Because of the open architecture, it's easy to get the malware onto Androids. Rootkits, rootkit, right? Root, meaning if you've got something that's rooted, it's owned, it's completely owned. Two types of rootkits, user mode and kernel mode. Both of them, if it's rootkitted, there's no sense in salvaging the system in most cases, because you can do basically anything with a rooted system. And a lot of malware today runs, it's fileless malware. It doesn't write anything to disk. It's all running in memory. Like Meterpreter. Anybody ever use Metasploit much? Meterpreter is it's like a Swiss Army knife application within Metasploit. It's great for running fileless exploits. So as soon as, because what most people do when they get infected with something, you go and turn off the machine, unplug the machine. Well, as soon as you did that, you just destroyed all evidence. Nothing was written to disk. So you start the system back up again. Everything looks legit, right? And then it's owned again. What the hell, right? Because the attacker knows what they did, and they're using probably another system to pivot into that system anyway. So they still have access to the system. As soon as you bring it back up again, they're going to own it again. So don't shut off systems as part of your first step in incident response if you can help it. But rootkits, bad. Even taking it off the network sometimes, will trigger the attacker. I mean, it's built into the code that when you unplug it from the network, it's lost network connectivity. It's not pinging home anymore. It'll delete itself from the process. So yeah, maybe. But if it's not propagating, why delete it from the network? If something's not propagating and it's just active and it's not causing a disruption, leave it there until you can get somebody to forensically look at the system, do some live forensics. And you can do some simple commands, like one of the first commands I do when I'm called to a live forensics is just netstat. Netstat, let's just see what active connections we have running. If any of them, that'll give you a good indication if something's going on. Process Explorer. I don't use Process Explorer, but there's another one like Process Explorer that we run just to see those active threads that are running. Antivirus software. This is Symantec, came out a couple years ago and basically said that antivirus is dead. I don't know, there's like hundreds of thousands of new variants of malicious code that come out every single day. So the traditional signature-based or even anomaly-based antivirus software isn't that effective. What is effective more so is application whitelisting. And that's the same thing with networks too, by the way. If you're talking about DLP, data loss prevention, rather than going blacklisting, we typically do blacklisting. Let's just block all the ones that are malicious, as opposed to let's just enable the ones that are, legitimately good, that we validated as good. Whitelisting is always going to be more effective than blacklisting, but businesses won't let us do it because they want to make money. Stupid businesses.
What's the logic there?
It's hard to do whitelisting, and it's controlling. A lot of people don't want to go through the effort, like even just asset management. If I'm going to whitelist something, I'm going to have to figure out what legitimate applications are permitted in this environment and what are they permitted to access. And that's a lot of work that I don't think a lot of people want to do. What's that? It's true. Yep.
And in order to win this, they have to know what they're doing that's legitimate.
Yep.
And most businesses I've encountered, they have no idea everything that's going on.
Right. But if you went, just imagine if you actually did invest the time and the effort to actually go through all that and then build processes where, you know, when things do change in the environment, that I can accommodate those changes or have some method, maybe to be alerted, like there's a new network connection that appears like it's coming from a legitimate application. I should investigate this quickly and have some, you know what I mean? If you could figure that out really well, just imagine how much more secure you'd be if you went on the whitelist approach. Only allow what's permitted versus only block what's not. Yeah. All right, so we're doing good so far on time. Any questions? Any other questions? I love the conversations, though. Man, it's so much better than just standing up here preaching. Sure, I don't even know if I'm saying anything that makes sense. Server-side and client-side attacks, just to understand the difference between the two. When an attacker is attacking somebody else, attacking a server, that's the traditional direct approach. That's a server-side attack. Client-side attacks are tricking you into downloading something so that you'll run on your system. That's an example of a client-side attack. Just different types of attacks. Web architecture and attacks. OWASP is your friend. Code Warrior is a great tool nowadays that's come out. It's gamifying secure application development. I just ran into that with the client in Toronto. Actually, he's using Code Warrior. Really, really cool. Yes, because application developers for the longest time were thorns in our side. Them and salespeople. You know.
Still salespeople.
Still salespeople, but now we isolate them. You know, we just like whatever, get pwned, pal. But developers are like, you know, they're like in it with us, and so, man, I've had more fights about pulling application development, you know, standing access to prod servers than. But anyway, OWASP is a great place. OWASP, Open Web Application Security Project, is what OWASP stands for. A lot of great tools out there, and the cool thing about OWASP is OWASP was actually established and is managed by developers. So it's developers telling developers what kind of security things they should have in place. So good resource, OWASP, remember that. Applets, the only thing you need to know about applets is this is what's called mobile code. Sometimes when we use mobile code with clients, they think that we're talking about code that runs on mobile devices. That's not what it means. Mobile code means something that you download from somewhere else and run it on your local system. Client-side attacks, these are great for client-side attacks. That's mobile code. The code actually moves and executes. So Java and ActiveX are the two most common, and the ones that you'll see on the test. And you'll need to know the difference between Java and ActiveX, just at a base level. Java runs in a sandbox, right? It runs in its own environment, and it's supposed to be contained in that own environment. But Oracle, Sun didn't do a great job at a lot of this stuff. That's why you have to patch this thing every 15 minutes, right? Because they keep finding vulnerabilities and things keep jumping out of the sandbox. ActiveX works by digital certificates. So there is no sandbox in ActiveX control, and ActiveX just runs assuming that it's been signed by somebody that's in your trusted certificate store, right? Which you can compromise that too, but just understand Java and ActiveX and the difference between the two, right? ActiveX only runs on Microsoft systems. Java is not operating system dependent. It can run on anything that's got a Java virtual machine running on it. Okay? XML, extensible markup language, and SOA. SOA and SOAP are different. SOA, SOAP actually allows two computers to communicate with each other. Whereas the open or the oriented architecture is just an architecture for application development. Memorizing these things is plenty fine. XML is very because there's a lot of other ones, but these are the ones that will be on your test. I'm not going to go into too much detail on that. Polyinstantiation. So this is database security. So now we've switched from some of these security vulnerabilities, threats, and countermeasures, and high-level stuff, right? I mean, we didn't get into the nitty-gritty, the step-by-step on how to conduct those attacks, which is good because you don't want to be tested on that right now. So database security, how do you protect database security? One way, because you have multiple people, multiple systems, multiple applications, potentially all accessing the same database. One way is polyinstantiation. So every time a new user, a new system, a new call from the application needs to access something in the database, it would create another instance for that access. So two different objects, instances, but they would share the same name. They share the same. I think it's like a process and thread, kind of the same kind of relationship would be with polyinstantiation. Yeah, that's all you need to know for now. Inference attacks and aggregation. So inference attacks, so to limit the aggregation attacks, the difference in inference and aggregation, I would run every single query possible, get the results, and aggregate the results. So there's certainty in an aggregation attack. So the way to stop that, because I'm not deducing anything, I actually have the evidence to support it. In an aggregation attack, I would just limit the number of queries. That one's pretty easy to protect against, an aggregation attack. Whereas an inference attack, it's going to deduce things based on, I run this query, I run that query, maybe I run this query over here. I can kind of deduce based on the results of these 3 or 4 queries what the results would be if I ran this other query, which is actually the query that would contain the confidential information. That's the way inference attacks, polyinstantiation and diffusion would protect you against that. Data mining and data analytics. Data mining is typically very, 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 very large data warehouses. Exabytes, terabytes. I mean, what's after an exabyte?
Data?
Petabyte? Okay. That sort of data typically is used for identifying patterns of fraud. So financial fraud, credit card companies use this, use data mining extensively. Sometimes if I'm not careful, because I am collecting so much data, sometimes I can collect private data inadvertently, which then is pretty easy to find through data mining techniques. That's good enough. Data analytics. So today in our world, we're confusing, I think a lot of people confuse data analytics with machine learning with AI. Right? Totally different things. Data analytics really is just establishing a baseline of, based on the data and analyzing the data, where we typically use this is here's a baseline, deviations from the baseline must have a cause. And that cause could be an attack, that cause could be something's not working the way it was intended to, whatever. But data analytics, really, what's a baseline? This is really popular in like intrusion detection and prevention, right? Because there's 2 types of data, just like there is in malware, there's signature-based and anomaly-based, something that deviates from the norm. Data analytics would be used for that.
Evan?
Yeah.
I'm sorry, I wasn't paying attention, I was responding.
Oh, you weren't paying attention.
What was diffusing?
Spreading the data out amongst multiple data stores, databases. What is diffusing? What? That?
Oh, I talked to the...
Talk to this? Hello? I don't like that.
Easy.
Yeah, we're going to get more into that too on Thursday, diffusion, because diffusion is one of the methods used for encryption. Diffusion is, and confusion. It's another one, diffusion and confusion. We'll get a lot more into that. Good question though. Defense in depth, so other countermeasures. So countermeasures against some of these vulnerabilities that we talked about. Defense in depth is a big thing. Most people traditionally build a crunchy shell GUI center type of security architecture. What we want is, so like an M&M with kernel inside, right? That's how people build. It's all about the perimeter, right? But we keep poking holes in all of our perimeters, right? For email, for web access, blah, 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 blah. So what we want is more like a gobstopper, like defense in depth, network isolation, network segmentation. Assume that the attacker is already through your perimeter. What can they do? Right? So your critical systems, having them isolated, only communication paths that are required for that system to operate. That's, examples of defense in depth. Also taking that down to the application level and so on and so forth. I gave you, there's a methodology that we use. It's not in the book, but if you want to know more about defense in depth and some really good strategies, the NSA methodology is a really good one for adversary obstruction. It assumes that the adversary is already in your environment, right? Because we've seen attack after attack after attack happen through pivot to get to the data store. Like the target attack, didn't start attacking at the store, right? It actually started attacking at the DMZ. From the DMZ went into the corporate network, from the corporate network into the store network, from the store network into the cardholder data environment in the store network, right? So obviously the obstruction methods, the segmentation and isolation was not effective. The defense in depth was not effective in that particular attack. And that's common in all attacks. Because people are so focused on the perimeter, they don't think of, that. We do most of our pen testing, I think a lot of our pen testing now, assuming that we already have. It's a 10-minute exercise to get through your perimeter, right? I mean, phish somebody, find a single factor authentication thing hanging out somewhere. Trick somebody into downloading a piece of malware. There's a lot of different ways to get into the environment. We just assume that we're already there in most attacks now. Mobile device defenses, so MDM, mobile device management, lots of these things can be really dangerous if we don't control these correctly. In some of the controls that we look for, we don't like wireless access, public Wi-Fi, because anybody can sniff that. It's, a simple ARP poisoning attack replicates all the data you're sending to the firewall, to my system as well. It's easy to set up, access points that are malicious access points, and I'm just proxying all your data. Lots of things with mobile devices, but these are the things you need to remember for the test. MDM, network access control, 802.1x, authentication, remote wipe, encryption. Those are all things that we like to see enforced through policy through an MDM solution. There's a lot of different cool MDM solutions out there today. So that's it for that. We got 20 minutes left, and I just got started. And I don't really like this. I like encryption. Encryption, I think, is really fun because it's cool. I like history. Anybody a history buff? Yeah, the history of encryption is just amazing. How it's been used to win wars. It's been used to save lives. It's been used to, really to tilt the power structure of the world we live in. It's really cool. So. Who?
The Wind Talkers movie?
I've got some good movie ones for you.
Yeah.
Yeah, there's some, and I've got some other good movies if you want to watch too. The best book that I've ever read about encryption is Applied Cryptography by Bruce Schneier. So if you really want to know more about, yeah, it's a great book. Bruce Schneier's a genius. And the thing I like about Bruce Schneier is he's never kind of been out. He's never been in it for his name as much as he is to help people. A lot of people now in our industry are out there to make a name, make millions of dollars. Bruce has always been just a cool, I've just admired his approach. He's kind of out there now. Him and like Marcus Ranum. Marcus Ranum was kind of a pioneer too in information security. They just kind of think out here now. I don't know how much practicality you can find in some of their stuff, but great book. If you want to know and master encryption, great place to start is Applied Cryptography. These are key terms that you'll need to, anything with ology, at the end of it is a science. So cryptology would be the science of cryptography or secure communications, really cryptography. Cryptography creates messages with hidden meaning. Cryptanalysis is breaking encryption or trying to get into encryption. Cryptology again, did I do it twice? Oh, well, it's because it's different. Cryptology is cryptography and cryptanalysis. A cipher, cryptographic algorithm, plain text is just something that's plain text, right? We don't like plain text. We don't like sensitive information in plain text. Ciphertext is the encrypted message. Encryption converts plain text to ciphertext. Decryption takes it the other way. It's all pretty basic and easy to understand key terms, but you'll need to, if they're not simple, you'll need to memorize them. If they don't just ring well with you. So there's confusion, diffusion, substitution, and permutation. So these are the differences between the two. cryptographic algorithms today use one or more of these, right? Like AES, the Rindell algorithm uses all 4 of these. That's the new, AES is the replacement for DES. Like DES is breakable, 20-something hours it takes now to break DES in a standard computing system, or not standard, a distributed computing system, kind of a grid computing. So then they went to triple DES because of that. And who runs all of this is NIST. NIST holds a competition, and AES is what won the new. So the advanced encryption standard is the new acceptable for unclassified information too, by the way. I don't know what's used for classified information. So there are other encryption algorithms that, like the NSA and the government uses, that we don't even know about. All right, so anyway, confusion. Relationship between the plain text and the ciphertext should be confused or as random as possible. So randomness is very important. With confusion, diffusion means that we diffuse it, we disperse it amongst, and this will make a lot more sense when we talk about block ciphertext and stream. So block would be feeding one block into another block and then feeding that block into the next block. That's an effort to diffuse it, to diffuse the ciphertext amongst, or the plain text amongst the ciphertext. Ciphertext into more ciphertext would be diffusion. Substitution is just, like take the rotation 3 is a encryption algorithm, very simple, but an A becomes a D. Is that route 3 or is that route 13? Yeah, route 3. Yeah, Caesar cipher. Yep, exactly. But that's just substitution, just substituting. The Vignere cipher is the same way, just substituting one letter for another. Permutation, rearranging the characters of the plain text, just flip-flopping things, right? It's not feeding one thing into another, so that's how it's different than diffusion. It would be permutation. Substitution and permutation are often combined, but the point is with ciphertext, the thing that makes ciphertext potentially more easily breakable are patterns. Any patterns. So most of these are meant to destroy the pattern, destroy any potential that you get the plain text from the ciphertext. In Thursday, we'll talk about some cryptanalysis attacks against ciphertext. We'll talk about how not you and not me, because we're not, well, I don't know, maybe some of you are mathematical geniuses, but I'm not that smart to do much cryptanalysis. So cryptographic strength, so things to remember about cryptographic strength, that one is the work factor, that's how long it would take, how much effort we need to put into breaking the encryption or doing cryptanalysis. That's called a work factor. Now, AES has a computationally infeasible work factor, which means that they don't know. It would take so long that there's nothing that we really know how to do it. I've just told you DES, its work factor, just standard data encryption standard, it's probably better than that now, but it was about 22 hours was the work factor. This is important because, if the work factor exceeds the value of the data, so if I know it's going to take a year for me to break this encryption, and by then the data is worthless anyway, well then there's no use in breaking it. Kirchhoff's principle just means that the security of the encryption itself has nothing to do with the security of the algorithm. So advanced encryption standard, data encryption standard, Bluefish, Twofish, RSA, those are all open algorithms. You can go and look at how the math all works. Kirchhoff's principle says that the security of the encryption has nothing to do with the security or the closeness of the encryption algorithm. There's actually proof that it works the other way. The more open the encryption algorithm is and open to scrutiny, the more secure the encryption would be, right? There are some IDEA is an example, IDEA, I can't remember what it stands for, but we'll get to that one later, is a closed encryption standard, used, and it's actually even copyrighted. So other encryption concepts, so you've got monoalphabetic and polyalphabetic encryption ciphers. These are This is kind of going from basic to kind of where we're at today. This is all more history stuff. So monoalphabetic is typically just a substitution cipher, where you substitute one for another using one alphabet. Now, very susceptible to frequency analysis because we know that the most commonly used letter in the English language is E. So given enough text, I can probably pick out where the E's are, right? Which then, makes it. So that's called frequency analysis, the frequency of a letter showing up. A polyalphabetic makes that a little bit more difficult because based on the first encryption, the first usually rotation leads to the second rotation, which still is open to frequency analysis, but a little less. So it's a little less obvious, right? But monoalphabetic, just there's a rot 13, so rotation 13. So you just rotate the letters 13 spaces. So hello becomes this URYYB, and then you've got a cipher disk there, a polyalphabetic cipher disk. So, and sometimes they would rotate in the middle, but don't worry about that. But based on its first encryption, it would lead to the second. Does that make sense? Monoalphabetic and polyalphabetic. There's frequency analysis. So you can see the letter E. The least frequent is the letter Z and the letter Q. So given enough ciphertext, it would, just a simple monoalphabetic cipher, even a polyalphabetic cipher would be pretty easy to do cryptanalysis given frequency. So the exclusive OR, the logic gate, you'll need to remember this. So if this is on the bit level, right? Bits are either on or off. It's either a 0 or a 1. If the two bits match, it's a 0 in the exclusive OR in this logic cube, a logic gate. If they're different, it's a 1. So you'll need to remember that. And some people I've heard that they've taken the test because they give you like a pad of paper and a pencil. They've actually written this down first, so they can refer to it. But it is really important. If the two bits match, it's a 0. Okay? If the bits are different, it's a 1. And this is really easy, just taking just this logic gate, because this logic gate is then applied to math in all the current encryption methods or algorithms. But at a very simple, if you take, attack at dawn, break that into binary, and then use the key unicorn, and go through the logic gate, you've got an encryption, right? And that's how it works. Basic stuff, but that's fundamental for the other encryption algorithms. All the encryption algorithms used today. So more history, hieroglyphics were encrypted, and we still don't know what most of them say. They were just using symbols to represent, specific words and concepts and things. The Spartan Cytale was pretty cool. So in a Spartan Cytale, what you do is you'd write out your message. Actually, you'd wrap it around the rod, and you write down your message down the side of it, and then you'd unwrap it and send it with a messenger. And the key, so what would need to be used to decrypt it, this is a sort of a symmetric encryption algorithm, would be a rod of the same circumference, right? So if I didn't have a rod of the same circumference, when I wrapped it around a rod, I wouldn't know what it said. So that, very basic. I don't know how effective it was, but that's what the Cytale was. Caesar cipher, we talked about the Caesar cipher. That's a ROT3 encryption, so you just rotate. It's also a modulus. So modulus means that it rotates back on itself. So, modulo, sometimes they call that. So, a Z then becomes a B. Right? It just rotates back through the alphabet. Yeah. Rotation ciphers, I think, what's ROT 13? Why is ROT 13 seems, news groups? News, do I have it up here? Who? Oh, use that. There you go. The Vignere cipher. So the Vignere cipher it's a polyalphabetic. You've got one alphabet over here, one alphabet over here. One is used for the key, and one is used for the message. And where they meet in the middle is the encryption. And that one looks like this one. This is the Vignere cipher. So, maybe, and it doesn't matter which way you go, they'll end up being the same ciphertext. But that's the Vignere. You can see the rotation and the monoalphabetic stuff. all even encryption, none of them are used anymore, really. I don't think, unless kids are using them or stuff, because they're all very breakable, especially given the computational power that we have nowadays. Cipher disk. So the cipher disk is there. Two concentric disks. So two concentric disks is a polyalphabetic cipher. So the cipher disk is a polyalphabetic. That one's one from the Civil War. This was a polyalphabetic cipher that was used during the Civil War. Yeah, that's about all you need to know about the cipher disk. Jefferson disks, they didn't find that until not that, I don't think it was all that long ago when they discovered the Jefferson disks. But the disks would be, lined up, and where they lined up ended up, being the key. So you'd rotate the disks. It's a polyalphabetic cipher. Again, but that's a picture of what the Jefferson disks look like. And I don't know how much of the history is actually testable. It's just cool. You know what I mean? So knowing how the Jefferson disks work with, what's the word, specificity or whatever, that wouldn't be testable. Just kind of cool stuff. And it is, in the book, there might be some like what's a rotation 3 cipher, something like that, but they won't refer to much beyond that. Book cipher and running key cipher. So a book cipher would actually use books, right? Page number, paragraph number, word number. So you'd get a bunch of numbers, and then you'd go get the book, and the key would be the book. So you go find the book, page number, and write down that one, and what have you. And that's how those work. Running key ciphers just use whole words rather than individual letters. So the book cipher would use the letters. Code books. Code books would be using. So maybe I'd refer to him as Eagle 1, and refer to you as Owl 7. You know what I mean? And you assign code words to specific things and objects, and that would be your cipher. One-time pad is the only encryption algorithm that's been mathematically proven to not be. You can't break it, as long as the certain rules play out. One rule is, so the way it works is you and I would share a pad of essentially keys. The pad has to remain secure. You never reuse the pad. It's a one-time pad. So I would encrypt the message. You would then use it to decrypt it, and then we'd go to the next page. Right? And the third is that the pad is truly random. The data on the pad. If those three things are true, then you can't decrypt a message with a one-time pad. So paired pads, random characters, set amount of characters per page. One page is used to encrypt the data, the same page at the receiver. So this is a symmetric encryption algorithm. Symmetric means the same key that's used to encrypt is the same key used to decrypt. Asymmetric encryption algorithms is like public-private key. So they're a paired key, but it's not the same key. We'll get into all that stuff later too. So pages are never reused. It's the only encryption method proven to be secure as long as those three things remain true. Truly random. The pads are kept secure. We don't reuse pads. Thing is people get lazy and they end up reusing. That's the only time this has ever been. The Rosenstein, I think, maybe it's in here, maybe it's in the book. But there was one time when Ethel and who's the other guy? Julius. They were busted because they were Russian KGB agents, right, in the United States. They were busted because they reused the pads. So, pretty cool. One-time pads, Burnham cipher, so this is just a machine implementation of the same encryption algorithm. First known use of the one-time pad, Gilbert Burnham, AT&T. There were a lot of smart people there. One-time pads were then, so the one-time pads then would use that logic gate too, and then would XOR with the text, the zeros and ones. That would be an encryption algorithm. Project Venona, cryptanalysis to break the KGB. Oh, maybe this is it. Yeah, Rosenberg, Ethel and Julius Rosenberg, because they reused the pads. That was Project Venona. So the U.S. knew that something was going on. They just couldn't figure out what. They couldn't figure out what the messages were, and they weren't going to be able to prosecute. So they found out that they were reusing pads, which then made cryptanalysis possible. Here's some good movies. What's life without movies? So U-571 was the Enigma machine. So was the Imitation Game. There was also an attack on the Enigma machine. I can't remember what All Queen's Men. I don't think I'm guessing it's probably Enigma too, because Queen's Men, that would have been going back to Bletchley Park and all that stuff. Good stuff. Good movies. Encryption's cool. Hebron machine in purple. These are cryptographic devices. These are not cryptographic algorithms per se, but these are devices that have been used over time. So you would type it in. This is not a rotary device, a whatever. But you type it in, and what you'd get on the other side would be the encrypted text. They would type in the encrypted text and get the plain text back. Rotating motors. That's the word. That's not the word I'm looking for. But anyway, there's a name for that device, but it'll be in the book, and it won't be testable anyway. I thought it was just cool. There's Enigma. So Enigma, a lot of stuff about Enigma. Enigma isn't necessarily testable either. It's just very cool. It's also in the book. But Enigma was a World War II German encryption machine. A lot of cool history around that, and us, the English and, actually it started with the Polish. The Polish were the first to kind of start the cryptanalysis, and then the English joined in, and then a little bit US, and we were able to eventually crack it, but we had to capture one. So interesting stuff. Sigaba was our version of the Enigma machine, so it was the US version of the Enigma machine. Supposedly never broken. You can see it's a big, huge, heavy typewriter. This isn't something you're going to carry around in the field. This is something that's going to be mounted somewhere. Purple, this was the Japanese encryption device. Actually, it's not a rotary device. It's circuits. What do they call it? Switch hardware, phone switch hardware. This one was cracked. And it gave us advance warning of an attack on Midway, which is, again, just kind of cool stuff, right? I mean, we cracked this. We were able to determine that when the Japanese were attacking Midway, so we were able to prepare, which is really cool. Cryptography laws, this will be testable. Wassenaar Agreement. Wassenaar has largely been replaced. COCOM has largely been replaced with Wassenaar. Wassenaar is a current agreement. Originally, it was meant to restrict the trade of intellectual property, and they fit encryption into intellectual property. So it would restrict the ability for us to use. So, like, let's say that we had a business unit in China. There were certain encryption algorithms that we couldn't use to encrypt data that we sent to China, right, and vice versa. And we weren't able to share encryption algorithms. Yeah.
So what about it is best?
The name.
Just the name, and knowing it came after COCOM, or
the name, and that it I would say just basically what's right here. Yes, it did come after COCOM. It's used to restrict the flow of cryptographic information, but it's less restrictive than COCOM. COCOM was a Cold War law. So Wassenaar is still very much in effect today. Replaced COCOM. It relaxed restrictions on cryptographic exports. So I think if you know those things for the exam, essentially what's on here should be fine. Holy balls. That was a lot of stuff. All right. Any questions? Anything? I tried to go fast, so I tried not to go too deep into too many things and whatever. So that's all we have for tonight. We're going to pick it up right where we're at now. So we went through the history of encryption. We went through just Wassenaar and COCOM. Those are really the only two encryption laws you have to remember. And then we're going to get into the actual encryption algorithms. So we're going to get into DES, triple DES, AES, elliptic curve cryptography, public, private encryption, all that stuff on Thursday. Thursday, I'm planning on going kind of as fast as I did today, because we only have Thursday and then Tuesday, and then we get another break. Right? So I want to get through all of this domain by this Thursday, hopefully. Right? So about the same kind of slam of information, but it should be fun. And we're up to page 160 now. If you are following along and want to keep up. Thank you, guys.
you.
Everybody?
Good stuff.
I think we,
Like 8 to 15
did good.
sprints.
Yes,